All right, everybody, welcome back. Well, up next, we have Jason Shirk, Dave Weinstein, and Lars Obsted from the SWI Tools team who are going to talk to us about fuzzing. So take it away, guys.
Great. Jason? Thank you. Afternoon, everyone. So we're on the SWI Tools team. Our job is to create and maintain tools for SDL compliance across Microsoft. I particularly own Fuzzers. Dave is one of my developers, and Lars is my principal manager. What we really want to talk about is when do we know that we're done fuzzing, or that we've got a reasonable assurance that we've probably found most of our bugs. But you have to answer some other questions to get there. We have to know the approach that we're taking. We have to know what we're looking for. And then we can really, based on some of those things, decide on if we fuzzed enough and to know how much is enough. So myself, I came from the telecom industry a little while ago to Microsoft, where I previously did penetration tests. I wrote documents like the SDL, did MSRC type work, and across the whole gamut. And in coming here, I got the opportunity to focus a little more on an area that I'm really passionate about, and that's fuzzing. And so there are a lot of different ways that we can really get into this. First thing that we have to do in fuzzing is we have to define our target. We have to decide what tools are there, what tools are best for our target. And in deciding that, within Microsoft, we have a number of tools for fuzzing, as well as there's a number of tools outside of Microsoft for fuzzing. So we held a little competition internally that we'll be talking about, and we'll actually be handing out some awards here on. And then what's most effective based on the answer to the other questions. In defining the target, we have to really drill in on what we are actually trying to fuzz. Web service, protocol parser, file parser. Also, it matters whether it's binary or whether it's text. And in this, if you're fuzzing a zipped file type and you don't uncompress it and you go and you flip random bits, you're not really fuzzing your parser per se. You're just messing up your zip, and you'll never get the penetration that you're looking for. And it can be difficult to get past some of these initial areas, and we have to be kind of smart how we get past them. We'll talk about that in a couple of minutes. As far as the types of tools, dumb fuzzers are pretty easy to build, and for, of course, the developers who build them, they're easy to use, though not necessarily for everyone else. Yeah, they're cheap, right? But they can find a lot of bugs. We don't have to spend necessarily a huge amount of time building these fuzzers if we really understand the parser or the protocol or whatever it is that we're trying to fuzz. And it really is the preferred method in the industry, and it still finds most of the bugs found by fuzzing today. Smart fuzzers, on the other hand, have a high cost of entry, because you not only need to understand how to change maybe a format that you might already have, but you need to be extensible. You need to be able to describe formats. There's more work that goes into it. You're building a language as opposed to building a simple bit flipper. But you can get better penetration. Can find different bugs as well. There's also the difference between generation fuzzing and mutation fuzzing, or mutational fuzzing. Generation fuzzing, you go and you create from scratch, as opposed to mutational fuzzing, you're changing something that you already know is good. And we'll see some examples of that in the participants at the Fuzzing Olympics. So in a dumb fuzzer, we're really just flipping bits, mostly, right? Or we could be, and it might be random, it might be sequential. If you've got a small enough file type or a parser, you might just start at 0000 and go to FFFF. And that could be sufficient, and you know that you've hit most of the areas, at least from a simple state that you're going to hit. But you also might just inject random garbage. It's amazing if you go out there and you have something that's never been fuzzed before, and you just throw as much crap at it as you possibly can, what's going to fall over. A lot of the services out there that haven't been fuzzed are very fragile. And so that's something to bear in mind when you're looking at a product that you might be trying to do a penetration test on, or some analysis for the SDL. Be sure that you hit all of your services, and not only the ones that you think that you own. But they can still be very effective, and it really is a very good ROI with dumb fuzzing. When we move into smart fuzzing, we run across some other issues. Not only do we have to essentially build this language where we can describe what it is that we're trying to fuzz, as opposed to just going and flipping some bits in some areas, But we have to be careful about how we test within that definition framework also. MSO 7017, the famous, pointer exploitability. This had to do with ANI headers, or ANI-H. If we had one ANI header, everything's good, everything's happy, right? Second ANI header, all of a sudden it's exploitable, and that's bad. We absolutely don't want that. But, from a developer's perspective, they think, well, who'd ever want to insert a second ANI-H? That doesn't make sense, right? Enter the bad guy hacker, and nasty things happen all over the world. So internally, because I own the fuzzing space for Microsoft, I came in about 8 months ago and I saw all these different tools that we had. We have mutational fuzzers. We have generation fuzzers. There's a constraint solver, which works entirely differently. It operates a section of code and goes through and tries to solve every path that it sees. There are external tools. Michael Eddington's on contract for us right now, so we use Peach in the Fuzzing Olympics. But we gave everybody the same notification on 2 parsers. One was binary, one was text. Neither had been publicly released, or publicly fuzzed, privately fuzzed, anything like that. One of these came from an acquisition that Microsoft made, and one was developed internally. And what does this really tell us about our bang for our buck? We should only really be investing in smart fuzzing as much as necessary to get to the target. Right? We've got to do our CRCs. If you've got a compressed file format, you have to decompress it. If you have other fix-up that you need to do, you've got to do that initial fix-up. But we're not creating a whole language to do this, right? These are fairly simple things. It's easy to go out and create a hash. It's not bad. Additionally, picking the right set of templates can increase your fuzzing effectiveness by double. Pretty bold statement, but we've seen it again and again and again. By taking your template set for generational fuzzers, figuring out what a min set really looks like, or a minimum number of tests that covers the maximum amount of code, you double your effectiveness. Fuzzing Olympics, we saw it. Also, Gavin Thomas out of SWI UK, which he's on a sister team to my team, did a lot of really great research into this. As an example, what he presented, across 500,000 iterations, File Fuzzer with a large template set found 31 bugs, with a reduced template set, 60 bugs. We also know we need to diversify. Running a single fuzzer or a fuzzer with a single approach is not going to find all of your bugs. Just hands down. So we've got some particular recommendations around Sage. Sage is a good thing to use because it works differently than everything else. It's the only constraint solver that we've got internally, and there's some other like I said, the research has been published publicly on how it works if you want to go and build something similar. But it can really help us to boil down the ocean, so to speak, to a more chewable or more drinkable piece in that case. FF to Sage, for those who are internal, is a new tool. You should have gotten an email on it on Fuzz Talk talking about what this does. Single-click integration with File Fuzzer, but you can use it with a fuzzer of your choice. And once you've gone through these steps, you've decided what fuzzer you're going to use, go ahead and fuzz away, find bugs. It's what we all like to do. We all like to break things. But once we've started fuzzing, we need to know what we're looking for. And for that, I'm going to turn over to Dave Weinstein.
Thank you, Jason. So my name is Dave Weinstein. I'm a developer on this team. For those who are watching this on MSDN when it comes out and are not familiar with Microsoft's structure, microphone please. Sound check. Can you hear me now? No.
Make sure the green light's on your...
Bill? Sound guy. Testing 1. Testing 2, sure. They were very careful and did a sound check before we got on stage. Okay. So my name is Dave Weinstein. I'm a developer on the same team. For those watching on MSDN who are not familiar with Microsoft structure, that means I work for Lars and generally work against Jason. And what I'm going to talk about is how we look at the results. Where do we find the faults when we fuzz? And the first thing we need to do is, did it work? If we don't know what we're getting, we don't have any results worth using. How do we know that our fuzzer found something meaningful? Now, traditionally, when we're talking about an application, we're really talking about two things that happen. Either it crashed or it hung. Now, the good news for us is that we're really good at detecting something crashed. It's pretty obvious. But we need to know that we found the right crash, and we need to be able to correlate that with the bad data. We want to be able to know that this file caused that fault, or this network packet caused that fault, or this SOAP request caused that fault. Saying, oh, we read 30 files and something bad happened somewhere is not a meaningful metric. And we want to make sure that our crashes happen as soon as possible related to the bad data, and we want to make sure that we can define what constitutes a hang. It's certainly possible that I have an application that is going to spend a lot of CPU time legitimately. So the first thing we want to do is we want to make sure the software dies fast. And one of the classic problems in this is any kind of heap corruption. Anyone who's done any significant project that's run into memory sprays has run into this. You'll get a crash that happens 5 minutes and 3 libraries over from the actual fault. You want it to happen as fast as possible. For people working on Windows, the Windows platform, that means you want to use page heap. You want that first memory corruption to hit a guard page and blow up. Then you'll get your crash, and hopefully you're proximate to what actually caused the problem. Additionally, and this gets a little bit to one of the earlier talks, you have to evaluate first chance exceptions. If you are wrapping something bad in a try-catch block, you've made things worse, not better. That means if you're monitoring your code in real time to look for problems, you need to catch dangerous first chance exceptions, because the fact that you wrote to invalid memory, but you caught it, doesn't make you safe. Finally, you need to be able to specify a hang for your application. What is the normal CPU or memory footprint for this application? Because again, if I'm doing a very large mathematical problem solver, I may allocate a large chunk of memory and spend a lot of time crunching at it. On the other hand, if I'm Notepad, that's probably not the case. And then again, in real time, you want to monitor for CPU or memory spikes so you can catch them. Now that's good, but we're going to get a lot of noise. If we're running a lot of tests, we're going to get a lot of crashes. Again, Microsoft tends to do things on a very large scale, so we're very sensitive to scaling issues. But even on a relatively small project, if I've got 500 or 600 crash dumps that a person has to go through and try and triage, that's very expensive in terms of staff time, and it's more likely than not going to happen. And the problem, and this is something Jason alluded to in the previous presentation, we had one set where we had all these unique bugs, and when you collapsed them down a little bit, most of them were the same, or a large chunk of them were the same. And the reason is there's a flaw in a low-level function that's the actual bug. And there's, say, 3 or 4 or 5 or 10 different code paths that get you to that function. You want to be able to recognize, here's my bug, and these are all just manifestations of it. So how do we find it when it happens through multiple code paths? And oh yeah, we're doing a good test pass, so we're running on multiple machines. So we have a solution, and the solution is we're going to take a hash of the stack, and we're going to say this hash correlates with this bug. So if I see this hash, I probably have this bug. Well, that solves part of our problem, but it doesn't solve the whole thing. It doesn't handle the case where I've got one flaw and 15 different code paths that hit it, because the hashes are going to be different. So a better solution is we create 2 hashes. We create what we call a major hash, which is the most recent 5 frames of the stack. And we exclude the offsets. And the reason we exclude the offsets is if you recompile and the offsets change slightly, we want them to end up in the same bucket. We also want to be able to drill down into detail and say this one is a specific unique crash, this code path. And so that we have what we call the minor hash, which is the most recent 64 frames of the stack hashed, and we also hash the offsets. Now, one other thing we do as a refinement of this is we have a list of symbols that we exclude from the hash, because if you actually look at a stack trace on certain error paths in Windows, you'd realize that the bottom 5 frames, the most recent 5 frames of the stack in a lot of cases, are entirely in your error reporting code. If you don't exclude those, the hashes of every bug would be the same. It's technically a hash, it's just not the useful kind. So great. Now we know what crashes are unique, but there's a problem. One of the reasons that fuzzing is such a good tool in software development is that it doesn't actually require security expertise. It is a purely empirical and pragmatic tool. We know if we do this, things blow up, and things blow up in interesting ways. And while we would like all developers to be aware of security issues, it is neither possible nor reasonable to insist that everyone become a security expert. For one thing, I would like the guy writing the medical software to be an expert in medical software. I really want the person writing the flight control software or the airline software to be an expert in real-time systems. I really don't want a garbage collect happening at the wrong time. So if we've got this one level of expertise that we know we need to have happen, we cannot reasonably assume that these developers also have to keep abreast of exploitation technology, of new trends in security, of new trends in mitigations. We'd like for them to be aware of it. But you cannot reasonably expect people to pull up two specialties all the time. So now we have a problem. We've got down to a set of unique major bugs, but we don't know how bad they are. And what's worse, our traditional metrics in software development don't work. Traditionally, the way pretty much every software development company decided what bugs to fix was how likely is the customer to hit it. If it happens 30, 40, 50% of the time, you have to fix it. If it happens one time in 10 million, odds are someone's just going to ship the software. And if you went back 10 or 15 years ago, or in some shops even today, and said, hey, I've got a bug, it crashes. Well, how do you get that to happen? Oh, well, if you give it this deliberately malformed file, it blows up. Yeah, right. So don't do that and ship. And off it goes. So our old metric really doesn't work for fuzzing. So we can't have security experts all the time, but we want people to be able to realize that some bugs are more equal than others, and we need to fix them. So how do we do it? And how do we make the most efficient use of the security expertise we do have? So we're going to expand our bucket a little bit. We know that we can do machine analysis of the crash. We have a crash dump. We have a debugger. We have a compiler. There's something we have to be able to do. And we know some things. We know that there are certain types of crashes that we outright deem to be exploitable. If you've got a write AV, it's exploitable. If you get data execution protection violations, first of all, thank you for opting into DEP, and second of all, it's exploitable. Actually, technically, you're probably already exploited. The same thing goes for an access violation on the instruction pointer. Must fix these, they're exploitable. There are some types of crashes which are probably not exploitable. I don't want to say never, because somewhere out there, someone's coming up with a way to prove me wrong, but divide by zero is probably not exploitable. Now, note that if you're a server out there, and I can make you divide by zero at whim, that's still really bad for you, but it's better than my being able to run arbitrary code. And there's still going to be a lot of crashes that our machine analysis can't solve. We're just going to have to say, a human needs to look at this, I don't know. And now that we've talked about how you should fuzz, and how you know how bad it was when you got there, Lars is going to talk about what happens and when you know you're done.
Okay. Is this one working? Yeah. Okay, good. So let's turn that one off. Okay, so my name's Lars Opsted. I'm currently the group manager for the SWI Tools team. And one of the first things that I had to do when I came to the SWI Tools team was we had a little problem in Vista where we needed to basically fuzz all of the parsers in Vista. So that was what a lot of the data that we're going to talk about here in this last section of the talk is. So when to stop fuzzing? It's a problem that plagues a lot of people. I mean, one of the problems is the external researchers are just going to keep fuzzing. They've got lots of machines and they'll keep running until they find something. Unfortunately, we have a schedule to actually release some software and decide when we want to stop and fix some bugs and things like that. So trying to give you some more informed numbers as far as when it makes sense to at least pause your fuzzing and maybe either fix bugs or go off and try a new approach. So there are different ways you could decide this. Arbitrary numbers, 100,000 should be familiar to a number of people here, but you might want to go a bit farther than that. When do you stop finding bugs? And to know when you stop finding bugs, you need to know when you're going to find your first one, because if you're finding bugs, in some ways it's easier to know to keep fuzzing. It's the bigger problem when you're not finding bugs. And basically try to predict when you'll find your next bug or ultimately your last bug. And maybe you could use some complex formula based on either how complex the file parser is, how large or how many templates you have, or some other more complex formula. But anyway, we'll be looking into a few things here. So as I said, I spent a lot of time on Vista fuzzing. We spent about 14 months fuzzing Vista, where we fuzzed over 250 parsers with over 300 bugs fixed and 350 million total iterations run. So based on this, we could say, well, run 1 million iterations, and then you're probably good to go. Well, maybe not. So before I go into a lot of the stats, I want to define a few things, because I'm going to be showing a number of charts that may be confusing without having clear understanding of these. So a parser I've defined as a section of the code that consumes a file. So basically that acts on a file, that interprets it and does different things based on the content of the file. A bug is a reproduced failure that's actually filed in the database and can be fixed by the developer. An iteration is a single fuzzed file loaded into the parser. A crash is an automatically detected failure grouped on the distinct call stack, as Dave was describing. And then a buggy parser is a parser defined as containing at least one crash found in Vista. So all of the numbers and all the graphs are based on what was found in Vista, not saying that these are, when we talk about percentages, it's percentages of crashes and buggy parsers in Vista, not in the total number of bugs that could have been found if we fuzzed an infinite amount of time. Okay, so first off, the effectiveness at various milestones. So this is, what this graph tells you is what percentage of the crashes and what percentage of the buggy parsers you would have found at each of the different milestones that I had mentioned before, as far as stopping at 100,000, 250,000, 500,000, and so on. So the 100,000 mark gets you up to about almost 3/4 of your buggy parsers, which is okay but not great. But it finds less than 1/4 of your total crashes. So that's really not acceptable as a bar. If you move up a ways, if you get up to the 500,000 level, you at least see there that you've found 92% of your buggy parsers. So at least the parsers that you found, if there's a bug in your parser, you found 92% of those. So that's a pretty decent number. I mean, at that point, what you're going to miss is going to be the rare case where you've got one very obscure bug. But the percent of crashes still lags at about 70% until you get up and around the 1 million mark, where you can get over 90% for both of those. And again, this is percentage of crashes and buggy parsers that were based on the findings in Vista, so not necessarily of the actual crashes. Looking a little more into this, if you look at the cost of each additional crash, the gold line at the bottom basically tells you what the total iterations per bug as you progress over the different milestones looks like. And the upper line is talking about what the cost is for the bugs found in the next milestone. So basically, as you move from 1.5 million to 2 million, it jumps up significantly. Part of that is that there are fewer parsers that run at that level, so there may be the quality of the data out there is not as good as the quality lower. But the good thing here is that even up to the 1 million mark, the cost for your additional bug is pretty consistently well below the 250,000 iteration mark. So that gives us some indication of how long we should keep fuzzing while we're finding bugs. So from those stats, we're recommending that at a minimum you should be fuzzing at least 500,000 on your exposed formats. And basically, as Jason had mentioned earlier, optimizing your templates based on your code coverage can double your effectiveness here. And you want to keep fuzzing while you're finding bugs. So continue a minimum of 250,000 since your last crash. That doesn't necessarily mean that you're running 750,000. I mean, it may be that you find a bug at 400,000, then another one at 500,000, another one at 700,000, and you keep going, and you may run to 1.5 million, but at least if you've had a period that's been clean, it's probably a good time to either go off and fix your bugs or consider using a different approach. Maybe switch to a different tool like Secutest or Sage, or develop your own custom fuzzer as appropriate. But it at least gives you a point where for that tool you've probably found what you're going to find on this run. So I know a lot of you are probably thinking, wait, 500,000 doesn't seem enough. I mean, it gets you the 92% for the buggy parsers, but as far as the crashes, we're still below the 70% mark. I mean, 69%, that doesn't sound like a very solid number. once we add the 250,000 sliding window, it actually moves our percentage of crashes up from 69% up to 91.8%. So almost the same 92%. And if we increase that sliding window to 500,000, so you would wait 500,000 for each one, then that only gets you up to 92.4%. So relatively small gain for that extra 250,000 in your window. So that gives a fairly good indication that this is kind of the sweet spot on where you're at a good point to either stop your fuzzing and fix your bugs, or stop your fuzzing and try a different fuzzing approach. Is it better to fuzz longer? Certainly, but I mean, this is a good baseline to start with. So out of this data, we wanted to try to test our hypothesis as to seeing, okay, could we take a buggy parser and actually push it to the point where we totally stop finding bugs? So we had a lot of parsers to look at. We had some of them that found just a couple bugs, some that found a bunch of bugs, and so we figured let's take one that had a lot of bugs and fuzz it as long as we could. So after 4 months of fuzzing and 27 million iterations on one parser with 300 unique crashes, well, we kept finding bugs, and they were, I mean, it slowed down over time, but unfortunately it didn't look like we're going to find the last one. Now this is taking to extremes, and one thing to note is that on these, basically this parser was dealt with by removing it from the attack surface on Vista, so these bugs do not repro on RTM, so that's good to know. So we're not exposed on these. When we look at this in another way, as far as looking at the deltas between crashes, it staggers up over time, and the good thing here is that it does stay in the reasonable realm up until you get to somewhere in the 2 to 5 million mark, where we jump over the 500,000 between crashes, and ultimately we have a end delta of 1 million iterations, which worked out to be 5 days of a fairly fast parser app. So that's probably longer than most people are willing to wait for one more bug. But as an experiment, this is what we got. So as we look at this another way, we worked with Nachi Nagapan in research to try to figure out, okay, how does this work as far as the statistical model goes? And he actually looked at this and said he would like to publish a paper on this, but he basically couldn't do that because it was such a good fit for the cubic curve. He'd be accused of cooking the books to get these numbers. But this is an accurate representation. You can see the cubic curve versus the actual curve. For interest's sake, I put the equation up there. I can't say that I can defend why the coefficients are what they are. With a model, all you can do is say this is the model, not necessarily why. And I show the R-squared value basically gives a value between 0 and 1 on how well any given curve fits the model. I mean, so the cubic is definitely a very good fit there. Quadratic is also decent, and you can see a few others that are within the realm of close. As we looked at how this statistical model mapped to other parsers across Vista that had a large enough number of bugs that we could do a reasonable model, the cubic was fairly consistently the best model. There were a couple where it was number 2, and there was one odd parser that was totally different from the rest. I think that's a statistical anomaly, but so this is all interesting. Gives us hope for the future that we may be able to basically build out a model and give a prediction on how long you should keep fuzzing and how long it will be until your next crash. But at this point, I mean, this is basically just early research that we may build on in the future. So basically the results of this, well, it's a failed experiment. We were not able to find the last bug. At least I don't believe that we did. The statistical model, though, was a surprising find that it was that good a fit and that it was so consistent across the many parsers that we looked at. But again, before we can apply it effectively, we would need to do significantly more research. Now, as far as looking at the effect of the suggested guidelines that I gave earlier, stopping at 500,000 would only give you 35% of the crashes that we found in the end. Stopping at the 500 plus 250,000 would give you 59%, which isn't a great number, but this is an extremely long run and extremely buggy parser, so I don't know that that's... I think if you stopped at that point with your 176 bugs, you would be in a pretty good state to go to the development team and the war team and say, this parser doesn't belong in the code, it's too buggy, let's just get it out of here. But in any case, there definitely are still bugs beyond that limit. And then 500 plus 500 does give you an additional 20% there. And that's pretty much it for my section, so I'll pass it on to Jason to wrap us up here.
Great. Thank you, Lars.
Yep.
Mike? Okay.
Is this still dead? Yeah. All right. We live here? All right, great. Get to juggle two things in my hands then. So what does this tell us overall? We've kind of gone through the whole journey of, choosing our fuzzer or what we're fuzzing in the first place, choosing our fuzzer, what we need to watch while we're fuzzing, and kind of how long we need to go. The takeaways really should be that we need to invest up front when we are making those critical choices on what we're going to do. Be sure that you've got the right target identified and that you have a fuzzer that's actually going to get penetration to that target. And you should really, 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 please optimize your input as much as you can. So take your templates and minimize them if you're going with a mutational approach. You also need to diversify. We do need to use a mix of tools and approaches in order to be sure that we've found the most bugs that we can find in a reasonable amount of time. And this is different than what we said before, right? We said, well, go out and take this one approach and run it for this long, and you should be okay. That's really not the case. You need to go out, you need to have a couple of approaches, and you need to run them both for a period of time. If you've got too many bugs, maybe you should address either your release schedule or whether or not that particular parser should be in the release at all. We need to fuzz long enough. 500,000, and then the sliding window that Lars was talking about, meaning 250,000 iterations since the last bug that you found. So that may mean that you only run 500,000 times because you didn't find a bug in your last 250,000. It might mean that you run 2 million. But once you've gone 250,000 past the last bug that you found, in most cases, unless you're exceptionally buggy, you can be fairly well assured you found the majority of the bugs. And then we certainly need to continue to fuzz as we go through the effort of beta and releasing the product. We should fuzz indefinitely if we can afford to. So take a box, set it back in a room, forget about it, check on it every couple of weeks and see if you found something else interesting. Because just because we've stopped looking at it doesn't mean that somebody else is. And as a matter of fact, once we go beta and we go release, that's when everybody else does start looking on it. So if you don't want to fuzz it, that's okay. Somebody else will do it for you. There are a lot of people who have done a lot of work that we implemented into our discussion here. Would like to give a big thanks out to them, particularly Michael Eddington, as he doesn't work for Microsoft particularly, but we've talked to him about a lot of things, and he participated in the Fuzzing Olympics. He's with Leviathan, and then too many people at Microsoft to mention, but these are some of the highlights. And thank you for your time. Happy fuzzing.